Okay, welcome everyone. So it's a pleasure to have Professor Raju Venugopalan. He is our senior faculty associate. So this is his first stint here, and some of you have been attending his lectures also. Raju is an expert in QCD, in particular, one of the experts in this exotic, very interesting phase of matter, Quark-Gluon Plasma, that we'll hear about. I think he was responsible for theoretically the understanding of a kind of a new understanding of the nature of this phase through this color glass condensate and several other important contributions to the subject. And he is currently the director of the Theory Institute of the Electron Ion Collider, EIC, at Brookhaven, and he's on sabbatical at Edinburgh as a Royal Society Wolfson lecturer, and he's also in the Simons collaboration on QCD with David and others. Pleasure to welcome Raju to tell us about QGP.
Thank you very much, Rajesh. It's been a real pleasure these last 3 weeks. So the idea for this talk came from a previous talk that I gave at a conference in Edinburgh called New Directions in Theoretical Physics. And then Rajesh told me that David was coming here. And I had happened to listen to a couple of talks that David gave on the occasion of 50 years of QCD. And he talked about all the many glorious things that came out of it, but somehow he was out of time by the end of that because of just the vast plenitude of such things to really go into depth into this aspect of asymptotic freedom. And so I thought that I would try to redress this in his presence here. So that was kind of the motivation and logic of the talk. And what a wondrous thing it has been. And so I try to illustrate that to all of you. So if you walk down a corridor in many university departments, you may chance upon this poster, which is the history of the universe. And starting, and it's actually already 25 years old. There's an update, but I like this poster better, even though some of the numbers are a little bit off on this. So it describes how the universe started from the Big Bang and went through a couple of phase transitions, nucleosynthesis, and then the cosmic microwave background radiation becomes visible about 300,000 years ago. But my focus is actually on this aspect of the evolution of the universe, which was made possible by QCD. And so the time scales are about 10 microseconds after the Big Bang, when the temperature of the universe was about 10 Kelvin, and so this is a scale of about 100 MeV in electron volt units. So there was a kind of a transition there that occurred, and so at some point, the universe was kind of soup of quarks and gluons, which was about a few centimeters in size. And then as the universe cooled, it went through some transition where these quarks and gluons condensed to form baryons and mesons. So baryons are objects with 3 gluons. So these are the 3 M&Ms that represent the valence quarks inside the proton. And there are also mesons as well. And so at some point, there was this transition occurred. And so the interesting question is, what is the physics of this transition? Is it a phase transition? Is a la vapor to liquid? And what are the properties of this matter? So that's kind of the outstanding question. So studying such problems in the strong interactions are almost as old as the strong interactions themselves. And so these are Fermi's notes on thermodynamics and statistics from 1953, where he speculates about what happens to strongly interacting matter as you vary temperature and the pressure shown on the x-axis in atmospheres. And he has these very interesting speculations that you have some condensed state of electrons, and then you have a degenerate electron gas. And then as you increase the pressure, you get a relativistic degenerate electron gas, and then he speculates that there might actually be a neutron gas there. So these are kind of the first hints of thinking about neutron stars, and then he has, as you increase temperature, you would get an electron-proton gas, and you have all these nice scribblings of estimates that he made. So this is kind of really, so it's almost as old as the strong interactions to start speculating what happens as you go high up in temperature and pressure. Now, subsequent to Fermi's work, in the 50s and 60s, there was this advent of particle accelerators around the world, in particular in Europe and in the United States. And they started discovering a hadron zoo of particles. So they started discovering lots of mesons, which we understand as bound states of quarks and antiquarks, the pions, kaons, rho mesons, zeta, and so on. And baryons, the delta, lambda, sigma, and then famously the omega minus, which validated the quark model. It was a prediction. And so there were all these particles, and as time went on, it seemed like there was an exponential increase in the density of such hadron states. So as you kind of start looking for heavier and heavier masses, the number of these resonances just seemed to explode. Okay? And so if you just said, well, what is the thermodynamics, a la Fermi, of such a very large density of states, would suggest that the pressures would start to become enormous because you have, this large density of states in your partition function. And in fact, there was a speculation by Hagedorn, just on statistical grounds alone, that you would have a limiting temperature, that at some point the universe would become completely opaque because the pressure would just explode. Okay, so this has ever since been called the Hagedorn temperature. And there's actually then, subsequently, there was a very nice paper by Kirsten Huang and Steven Weinberg, where they actually used the Veneziano model to actually say, well, if you take the predictions of old string theory, the Veneziano string theory, and based on some suggestions by Lovelace and so on, you could kind of vary things, and then you would get various possibilities corresponding to different critical temperatures. But in each single case, they found a critical temperature on the order of 150 to 170 MeV or so. And so this was then kind of a big puzzle. And in fact, it was alluded to in Weinberg's classic popular science text, which I read when I was in high school, somewhat later, and this was in 1973. I think the book was actually written in 72, just before it came out. And he has this great phrase there saying that thus our ignorance of the microscopic physics stands as a veil, obscuring our view of the very beginning of the universe. So that was kind of the perspective, that we don't understand, the early universe. We don't understand the microscopic degrees of freedom. And in fact, this paper by Weinberg and Huang is very interesting because they have all these speculations about what the early universe must be like, and they were all wrong, actually. So that was kind of, and of course, as we now know, it was QCD that lifted the veil and allowed us to peer back in time. So that was really a very important consequence. So I should tell, for non-experts, a little bit about QCD. So I'm going to go through some of its key features and then illustrate some of its consequences for our understanding of matter at high temperatures and densities. So QCD is the fundamental theory of nature's strong force. Its constituents are colored charge and quark and gluon fields. And it's a nearly perfect theory. So for the first time in human history, we had a theory with almost no parameters. So the only parameters are the quark masses. And in the limit that the quark masses are put to zero, it has this incredibly rich structure that is entirely emergent. It's not visible necessarily even from the Lagrangian, so it's a property of the theory. And so now we all take it for granted, but how this theory developed was really kind of a spectacular tale, and I think it's one of the great great stories in the history of science when the definitive history will be written. I don't think it has been of this theory. And there's a very nice analogy that due to Jeffrey Mandula, where he said, it's sort of it resembled how sort of a larva goes through various stages to become an iridescent butterfly. So there was this idea of the quark model, and it's just a purely mathematical construct to understand the zoo of hadrons. And then there was the suggestions by Nambu and others that you could think about these in terms of there could be some new degree of freedom called color as well. And then so there was this whole sort of discussion, which I won't go into, which eventually ended up in asymptotic freedom, and which is just the butterfly that we now know today. So the key features of the theory, the most striking feature was asymptotic freedom that really changed our intuition about how strongly interacting theories could behave. And the basic idea there was that as you go to higher and higher resolution scales, shorter and shorter distances, due to Heisenberg's uncertainty principle, that the coupling got weaker and weaker. So this is the latest update from the particle data book, which shows a whole range of experiments, starting from low energy experiments to extremely high energy experiments from a variety of different machines, colliders, which really show remarkably this behavior towards asymptotic freedom. So the coupling only logarithmically gets to be free. It's always interacting, but very, very weakly. And we now understand that the reason for that is because of the self-interactions of gluons. So unlike photons and QED, gluons can self-interact. And very importantly, the change the sign of the running of the coupling. So that was this tremendous insight. And so this told, so the idea is that things become very weak at short distances. And so what are the consequences at higher temperatures and densities? So a major consequence is that instead of things becoming more and more strongly interacting, as Hagedorn would have us believe, that what really changed was the release, as you go up to very high temperatures and densities, of the internal constituents of the hadrons. And so at asymptotically high temperatures, what you would expect is a weakly coupled gas of quarks and gluons. Okay? And so this is what, to use this poetic metaphor, would lift a putative veil on the early universe. And to the best of my knowledge, the first such discussion in terms of an actual phase transition was by Cabibbo and Parisi from 1975, just shortly after the discovery of asymptotic freedom, where they said they actually thought it would be a second order transition based on various considerations. And around the same time, there was also a nice work by Collins and Perry, where they suggested just that asymptotic freedom would also predict presence of quark matter at the core of neutron stars. And the argument is simplicity itself, that says that the density is proportional to the cube of the Fermi momentum. So as the Fermi momentum gets larger, as the density gets larger, the coupling should run as a function of the Fermi momentum. So at sufficiently high momenta, you should get a quark star. Okay, so that was kind of, so these two papers that came in quick succession, and that actually helped propel a lot of the quest to understand what's going on. Now, the other feature of QCD is its counterpart is quark-gluon confinement, right? That the fact that you don't see free quarks in nature is not a bug, but a feature of the theory. And so we had some discussion yesterday about the mass gap in Yang-Mills. But very simply put, that as you try to pull the quark and anti-quark pair apart, the tension between them grows, and it's some of, yeah, sorry, not the tension, the potential grows, excuse me. The tension becomes constant. the potential between them grows, so it goes linearly with the distance. And resulting in a string tension, which is kind of a large scale. And so it's about 1 ton weight, essentially, is the weight between these guys at a distance of 1 fermi. So it's a remarkably strong force. And so this actually gives an intuitive picture of confinement of color charge. And this is seen now in lattice experiments, which I'll talk about a little bit further later, is that if you try and put these two quarks in the lattice and you simulate QCD on the lattice, as you try to pull these guys apart, at some point, the tension is so great that you pop up pairs of light quarks from the vacuum. So this picture is such that as you try to pull these guys apart, that eventually they pop pairs up and then they form colorless hadrons. So that's kind of the simple-minded reason why you never see free quarks in nature, is that a vacuum has sufficient energy to pop up these pairs. And so you create colorless mesons at large distances, as illustrated by this lattice plot. So the consequence of that is, again, the converse at high temperatures, is that at low energies, we now understand intuitively why hadronic matter is interacting gas with mesons and baryons, as the lattice would tell us. And so these ideas, of course, owe a lot to Ken Wilson, who kind of pioneered the lattice simulations of gauge theories, in particular QCD. And there's been tremendous progress in lattice simulations at fine temperature and baryon chemical potential that I will come to shortly. Now, there's a third feature of QCD, which is extremely important, but is less talked about than these two, which is a property of the theory, which is handedness. So if you put the masses in the QC Lagrangian to 0, then the left and right-handed quarks behave like they're independent degrees of freedom. And so they have a handedness, which can really write down the Lagrangian as two separate Lagrangians, one for each. However, this symmetry, the apparent symmetry of Lagrangian, is actually broken spontaneously by the properties of the QCD vacuum. And for that, we owe the insights of this can be traced back to the work of Nambu and Anderson, but in particular Nambu, in this case of strong interactions, which led to him being awarded a Nobel Prize for this work. And so what this tells you is that the spontaneous breaking of chiral symmetry, in colloquial terms, tells you that the left and right-handed quarks, in particular, in this case, as shown, the anti-right-handed quark and the left-handed quarks, they march in lockstep. Okay? And so there's a certain amount of energy involved in keeping them there, and that's the energy that you see in this kind of Mexican hat potential, where the vacuum is not at say, its height, but at one of these different minima. Now, what the presence of quarks do is actually to tilt this Mexican hat potential a little bit to prefer one of these vacua. And that is what leads to giving masses to the mesons, which can be understood as Goldstone bosons of this broken continuous symmetry, which is chiral symmetry. So in fact, that we now know that without the light quark masses, if you just had a world without quarks, if you just have quenched QCD, that actually gives you a very large fraction of the mass of visible matter. And adding this little bit of quark mass, which comes from the Higgs mechanism, only changes this by a few percent. And in particular, the quark masses, in addition with the breaking of chiral symmetry, in addition with confinement, is responsible for the existence of 99% of visible matter and the interactions between these constituents, as described through this feature of chiral symmetry breaking. Now, what happens at high temperatures is that as you increase the temperature, this condensate melts. And in fact, it provides a kind of order parameter for some of the dynamics, which can be used to characterize the phase changes in this properties of this matter. And that's sensitive to the number of quark species or flavors, as we call them, the colors and the masses. So you can play kind of a nice game in this lattice world where you put the theory in the lattice and you vary the number of flavors and colors and the masses of the quarks, and you see very interesting different phases of that matter. And so as you increase the temperature, then what happens is analogous to the destruction of magnetization due to thermal fluctuations in a ferromagnet above the Curie temperature, that you kind of randomize these spins, and then you kind of lose the magnetization, which kind of goes to zero above. So that's one consequence of finite temperatures and densities, is a restoration of chiral symmetry breaking, and the description of the high temperature or baryon density phase in terms of order parameters related to the breaking of chiral symmetry and its restoration. So there's one other feature which is extremely non-trivial, is the non-trivial topology of the QCD vacuum, that we now understand the QCD vacuum to be this enormously rich and complex object. And in particular, there can be these instanton-like configurations which carry topology, winding number, that characterize the vacuum. And these are simulations, lattice simulations with pure gauge theories, which actually do simulations in Euclidean time, and you see such kind of localized instanton-like configurations, which are topological. Now, this topology is extremely important for our understanding of the real world, because without the presence of topology in strong interactions, you wouldn't understand things like the decay of a pi naught to gamma, for instance. So that's one very powerful instance. And in fact, there's this plot I like to show in talks, which is the prediction of Adler very early on for what the decay, the time scale for the decay of a pi naught. So this is time in 10 to the minus 16 seconds. And that's his prediction very early on. And this is the data over time. Okay, and so the data kind of evolve to Adler's prediction. And this is the most precise prediction in QCD. It's to 1% accuracy. In fact, the data, and so the little dashed line that you see, these are corrections to Adler's result from the theory. Okay, they have 4% corrections to Adler's result, and the data, at least until 2012, I should look for an updated plot, couldn't resolve between the two. Okay, so this is really quite a remarkable illustration. In fact, if you didn't have topology and you had massless quarks, the pi naught would not decay. Okay, so it would, I mean, the presence of quark masses will cause the pi naught to decay, but it'll be 3 orders of magnitude different from what is predicted. Yeah.
For the other people,
yeah. Thank you. Yeah.
At the beginning, there's a 3 sigma discrepancy between QCD and theta.
Right.
So don't ever believe in 3 sigma.
Oh, right. Very good. Yes. Right. That's a good point. The pi dot, well, I mean, you're measuring photons, and photons are always very hard to measure. And you're measuring the rate, right? You're trying to extract the decay rate of the photon. So I mean, right? So neutral pions, and then photons. Yeah. It's 10 to the minus 16 seconds, right? So it's the decay rate. Yeah, that's what 2012. So there are also low energy experiments in Switzerland at PSI, but then there's also experiments at Jefferson Lab as well. So there's a range of experiments that are because part of the goal is to test chiral perturbation theory now. So it's to really test the chiral Lagrangian and so the anomalous contributions to the chiral Lagrangian, and that is, a big field. People have computed things up to 4-loop order in chiral perturbation theory and so on. So, of course, this is not the only instance. The other thing we should mention is pi naught to gamma is sensitive to the number of colors in the theory. So NC equal to 3 is also a direct prediction. So that's also the direct connection to QCD, that it not only tells you about the anomaly, it tells you about the number of colors in the real world, and that's NC equal to theories. So the other very interesting thing that is related to topology is the mass data prime, which is almost entirely topological. So people talk about the origin of mass. Well, the eta prime is a remarkable object, which is heavier than the proton and is almost entirely generated by topology. In fact, the non-topological corrections, mass corrections, there are on the order of, again, a few percent. So it's almost dominantly a topological object. And so this, of course, follows from the great work of Toft and then later Whitman and Veneziano. So what are the consequences of finite temperature? That's more subtle. And so what the topology, the QCD vacuum, and in particular, what the pi naught to gamma tells us is about the quantum violation of an axial U1 symmetry of the Lagrangian of QCD. And so it's a quantum breaking rather than due to some spontaneous symmetry breaking in the case of the chiral symmetry breaking. Now, if this vacuum and if the quantum breaking can be understood as due to instantons, then there was beautiful work starting with David and Cal and Dashan, but also David with his students, Bizarski and Yaffe, who actually quantified, how this UA1 is restored at very high temperatures because the instantons go away, they're screened at very high temperatures, and so the instanton contribution kind of goes away and you kind of restore UA1 at sufficiently high temperatures. And there was a very nice paper by Pisarski and Wilczek where they actually talked about the consequences of UA1 breaking and its restoration on the phase diagram of QCD. It has consequences for whether the transition is first order or second order, depending on the quark masses. So this is a very subtle, interesting consequence. There's some very interesting lattice data, actually, which seems to show that instantons actually go away, but somehow the normalizations are off. So there's still some very interesting work to be done in that direction. So how can we study QCD matter? And this is a kind of a cute little cartoonish plot that my experimental colleague Peter Steinberg created about almost 20 years ago. So of course there was a Big Bang I talked about. There's lattice QCD I'll talk about in a bit. I mentioned neutron stars, so that was very clear. And then there was actual experiments on Earth, the most striking of which until some time ago was the Relativistic Heavy Ion Collider. So the Relativistic Heavy Ion Collider was collided beams of ions at 200 GeV per nucleon. So each beam at 100 GeV per nucleon. So that's 100 times the mass of the proton. So these are very ultra-relativistic ions. They're traveling at 0.997 the speed of light. So you're extremely kind of Lorentz contracted pancakes that collide, and they kind of boil the vacuum in the process, creating these high temperatures. So today is a very special day because it's the last day of RHIC, actually, February 6th. There's a ceremony at Brookhaven in 4 hours' time, or a little less than 4 hours' time, where there will be some button that some Secretary of Energy will push, ending this machine. So it had a long run. It ran for 25 years. It's one of the longest running accelerators. It was a remarkably versatile machine. And it actually had led to great insights and triggered a lot of advances in QCD. So in that sense, it's kind of a sad day. Sorry? Oh, so this is actually it's nice that you mentioned. So there was this is just to illustrate that you can actually see the RHIC ring that from if you're flying over it, that's kind of what it looks like, and you can actually even see it from space. So you can see like this little dot on Long Island. In fact, since 9/11, I think this this kind of picture was not was not very popular anymore. The idea of small planes flying over major nuclear facilities was seen as, so this is an anachronism in that sense. But anyway, so the bottom line is that this is the last day. It had a remarkable run, but the physics continues, and in fact, it's gotten richer and more diverse as we've gone along. So in all of these areas, of course, the Big Bang, well, we had some interesting discussion yesterday about some issues there, but that's not relevant for the Quark-Gluon transition. But in terms of lattice QCD, we are now in the exascale era of computing. So the computing power, even since 2000, has just exploded. So we are looking at exaflops computing, and that has also really it's put lattice gauge theory on steroids in terms of the space of what you can do, and I'll show you an illustration of that. There's also been tremendous progress in nuclear astrophysics and the physics of neutron stars from mergers in neutron stars and studying them through the gravitational wave signals. So there were some remarkable events of neutron star collisions seen through gravitational waves, but simultaneously also in the electromagnetic radiation signals and observational signals as well that you had. So that's kind of this new multi-messenger area of nuclear astrophysics, which is actually exploding. So it's really starting to really take off. So that's a very important area. And then, of course, the LHC has taken over where RHIC stopped, and undeniably, the LHC is a much more powerful machine with detectors that have tremendously greater capabilities. So the LHC is at about about almost 30 times the energy of the RHIC collisions, and so its capabilities are just enormous. So when you increase the energy, the scope of what you can do, as I'll show, increases enormously. So what's the logic is ultimately just like in condensed matter physics, we want to understand the phase diagram of QCD in the different regimes. So here's a plot of temperature as a function of the baryon density, which is loosely related to the baryon chemical potential. So the early universe really was almost baryon free. So it was really radiation dominated. And so the early universe kind of corresponds to this region here. And that's also the region of the RHIC and LHC experiments, where they actually look at very low baryon densities, with one caveat that at RHIC, you can also, the machine is so versatile that you could also run it at lower and lower energies. And as you start to run at lower and lower energies, you start to probe this region of the phase diagram in QCD. And there's also suggestions now, there's an experiment which should be starting in a few years, hopefully, if not sooner, at Darmstadt in Germany. So that's FAIR, that's a big machine there, which will collide beams of nuclei at much lower energy. So the idea is to look at cold baryonic matter at high densities, and so explore this region of the phase diagram. There's also a machine in Russia whose status is uncertain. And so the questions are, well, of course, we want to understand better the structure of neutron stars, and whether you can, as you increase baryon densities, a conjecture idea that you have a line of first order transitions ending in a second order transition that's a critical point. What is the location of the critical point in the phase diagram? Are there tri-critical points? Are the phases of matter, so they could be color superconductor at sufficiently high baryon densities, or so-called novel Quarkionic phases, where the matter is somewhere between deconfined and confined matter. So there's a number of different possibilities which are theoretically conjectured, which could be explored with ongoing experiments. Now, lattice QCD, as I mentioned, is on steroids. And what you do in lattice QCD essentially is you put the theory on a hypercubic lattice, which is, you can't really do that on the slide here, but that's an illustration. and you solve the theory. And of course, with thanks to Wilson's insights, you can, and that of Kreutz, you can actually solve the theory in computer. And you can, in compute thermodynamic observables straightforwardly, you can look at the pressure and the speed of sound as a function of temperature. So just to give you a sense, 150 MeV is about 1.75 trillion Kelvin. So it's extremely hot temperatures. So what's plotted here is the pressure normalized by the temperature to the fourth as a function of temperature. And in contrast to hagedon, so if you remember that catastrophe, what you see is that the pressure increases, but then it kind of flattens out. Okay? So there is a growth in the pressure, but it's not as dramatic as as was conjectured in Hagedorn's plot. And so you can also study. So this black line here is for zero baryon density, and these different lines are for increasing as you also study it as a function of baryon density. And you see the baryon density also raises the pressure as well as you go to higher temperatures. You can take the derivative of the pressure with respect to the energy density and compute the speed of sound. And you see that there's a kind of minimum in the speed of sound. This is relative to that of light. So the speed of light would be 1 in these units. And you see that it reaches a minimum, and then it starts to grow. And this is the limit that you would have for a free relativistic gas. So asymptotic freedom is telling us that, well, we will eventually get there, but you have to go to much higher temperatures for the theory to be really asymptotically free and weakly coupled. So this plot is telling us that the theory is strongly coupled at these temperatures, even though the pressure is telling us that one is experiencing some features of this deconfinement. So you see a release of latent heat having to do with resolving the quark and gluon degrees of freedom, but you're also, these quarks and gluons are not asymptotically free, they're strongly interacting, which should not come as a big surprise. So here's a remarkable plot, actually, which is very recent, where it shows now the lattice is so powerful that it can actually now compare to data. Okay, so so the lattice is just seen as something you could extract in thermodynamic properties, and then you have to kind of extrapolate a lot to connect that to experiments. So here's the temperature. So this is the critical temperature or pseudocritical temperature. So there's no genuine phase transition, but you can still define something in terms of the chiral order parameter. And so lattice QCD can compute this at 0 chemical potential to 1% accuracy. Okay? So we now know that the crossover temperature is 155 MeV plus 1 plus minus 1. So this is a fantastic result. As you go to higher baryon density, there's a sign problem in lattice QCD, which actually makes it challenging to do first principles computations. But they've made quite a bit of progress even there, and this crosshatch band shows you the results for, if you keep the energy density or the entropy density fixed, how TC behaves as a function of baryon chemical potential. And so this is the lattice result. And here's data that's extracted by looking at the thermodynamics of the produced particles that you emit in these collisions. So they can also be described in some kind of a thermal model. And if you extract that, you see that is actually in quite good agreement with the kind of the lattice results here. So of course, there's uncertainties due to the modeling of this, but again, the experimentalists have a fantastic job in terms of getting rid of all kinds of systematic uncertainties. Again, this is not a plot I thought I would see 25 years ago, that you can actually really start to make detailed comparisons between lattice predictions and experiments, confirming some features of the QCD phase diagram. Okay? And so this temperature is the hottest and densest matter on Earth that we create in these heavy ion experiments, and with the highest temperature in excess of 5.5 trillion Kelvin, over 100,000 times hotter than the core of the sun, and it's in the Guinness Book of World Records. Now, what are some of the features of this Quark-Gluon plasma that you create? The first is that it's a nearly perfect fluid. Okay? And so that was one of the big claims after RHIC was turned on, that you saw that the viscosity to entropy ratio, as I'll discuss, was extremely low, and so there was a claim that this is a perfect fluid. So what do we mean by that? And this is actually a very interesting topic, far more interesting than I would have initially thought. And so what happens is you have this heavy ion collision. These are highly Lorentz contracted pancakes. So it's really initially like a one-dimensional fluid. The pressure gradients are all in the longitudinal direction. And you can very simply describe its dynamics in terms of 1+1 dimensional relativistic hydrodynamics. And that's sometimes called Bjorkian relativistic hydrodynamics, following a classic paper. And that just says that the physics is like Hubble flow. So the change in the energy density as a function of time is proportional to the enthalpy density minus E plus pressure, energy density plus pressure. And then there's a viscous force term which opposes the expansion. So if you had a perfectly ideal fluid, it would have no viscosity at all. It would just respond directly to a pressure gradient with no resistance. So this is the resistance to flow, and that's normalized by the time. So if you want to say what is the degree of resistance of a fluid to a perturbation, that's then quantified by how big this term is relative to the first term. So that tells you how good a hydrodynamic system that this is. And that's just this thing divided by the enthalpy density, which by the first law of thermodynamics, you can write as the entropy density times the temperature. And then there's this factor tau from the denominator. So the key thing is this ratio here. So what determines how well a fluid responds to perturbation is not the viscosity per se, but it's a ratio of the viscosity to the enthalpy density or the entropy density. And so the definition of a perfect fluid is one where 8 over S is very small. Now, here's a really beautiful thing is that when you look at 8 over S, it's a remarkable thing because it really depends on two fundamental constants, the h bar, Planck constant, and Boltzmann's constant, times the relaxation time of a perturbation that you induce in the fluid. So if you perturb the fluid, how quickly does such an excitation relax, divided by some intrinsic time scale in the fluid, like a de Broglie length or time scale that the fluid possesses. Now, in kinetic theory, typically, the relaxation time of an excitation is much longer than the characteristic scale of the quasi-particles, the de Broglie wavelengths of that fluid. So you would expect 8 over S to be larger than 1. And so let's look at 4 such fluids: water, liquid helium. And these are very cold lithium atoms which have been released from a trap, which then expand. And you can ask, what is the viscosity of such an object? And finally, the Quark-Gluon plasma. So again, so 8 over S, 4 different fluids. And water has an 8 over S, which is in h bar, or the Boltzmann constant is about 8. So it's a fluid that flows reasonably well. And this liquid helium, which you think of as kind of paradigmatic as a fluid that is very lowly resistant to flow, it has 8 over S about 2. And then you look at cold lithium gases, and this is in a so-called unitarity limit when you're close to what's called the Feshbach resonance, when the fluid becomes very strongly coupled. And there you see that, the 8 over S is very small. It's much smaller than that of what you would expect from kinetic theory, right? Because the relaxation time is smaller than the intrinsic quantum time scale. And then there's a quark-gluon plasma, which is an even smaller 8 over S. Okay? So this is really striking. Now, the other thing I want to bring to attention is that the difference in temperatures between the two systems is on the order of 17 orders of magnitude. So it's very cold and very hot matter. But also the viscosities are vastly different. So the viscosity of cold atomic gases is also very small. It's 10 to the minus 15, while that of the quark-gluon plasma is actually enormously large. Okay? I'll come to that in a second. But so this observation initially at RHIC triggered a tremendous kind of activity and confusion in really thinking about, you know, how can you have such fluids which have such low rate or S, and what does that mean? There was some brilliant work following, of course, the remarkable paper by Maldacena on the AD-CFT correspondence, which many people here are expert in. But the connection to RHIC was really made clear by these folks here, in particular Damson, where he came up with something, an argument which is really simplicity itself. It's one of these things you see and you kick yourself that you didn't come up with this, you know. Which is he looked at, you know, the absorption cross-section of a graviton with a certain frequency in a black hole, and this can be expressed in terms of four-link correlator. It's a real-time correlator. It's an autocorrelation of two components of the stress tensor. And this is really essentially related to the Kubo formula and the zero frequency limit. So where for the viscosity, so this expression is really this absorption cross-section at zero frequency, again, divided by Newton's constant. Now, we know from Bekenstein and Hawking, the entropy of a black hole is the area over 4G. And so if now the absorption cross-section is on a black brane, which is just you know, given by the area, so then this object is given by the area. So you can put this all together very simply, and you get this result that 8 over S is 1 over 4 pi. Okay? And so Coftonson and Starnetz went further and boldly conjectured that this could be a universal lower bound. So 8 over S is, again, it's about 12 times less than what you would expect of a normal fluid, which is 8 over S of order 1 or greater. Right? So this was kind of remarkable. It got a lot of excitement because, you know, string theory could possibly be an explanation for, you know, or at least the brain world could be explaining what might be going on or how to think about such strongly coupled fluids. The reality is more complex, but anyway, it was very, very, very interesting. The other thing which I want to bring to attention, which is remarkable about perfect fluidity, is that the Quark-Gluon plasma is actually a very viscous fluid. Even though 8 over S is very small, it has a viscosity which is 10,000 times greater than pitch tar. Okay? And so this is a pitch tar experiment. It's the world's longest running experiment in Australia, where you kind of, it's really like watching paint dry, but on much longer time scales. So you'll try, so every 10 years there's a drop of this. It's to prove that this is actually a liquid and not a solid. And so every 10 years there's a little drop that falls into this beaker here. And the Quark-Gluon plasma is 10,000 times more viscous than this object, right? But remarkably, it has almost no resistance to flow. And the reason for that is that the enthalpy density is much greater than that of, you know, fluids that you usually think of. So the resistance to flow is very small. So it has a number of remarkable features, this fluid we create at RHIC. Okay? So what do you do actually? So you collide, you know, these nuclei at very high energies, and then what you look at is you look at the distribution of particles that come out, and you look at the distribution in the azimuth. So you have the beam here, and then you look in the azimuthal direction, and you look at the distributions of particles, and you look for variations in that distribution as a function of the azimuthal distribution. Okay? And what that is telling you is how the initial, you know, non-spherical nature of the collisions, right? Because you have actually nuclei, which are these pancakes, which have some distribution spatially, how that transmits to momentum distribution, right? So the efficacy of hydrodynamics can be described as given a certain energy density lump that you create, which has some spatial distribution, how does that transform through hydrodynamics into So that's the resistance to flow, right? So the less resistance to flow there is, the more faithfully it will reflect that initial momentum distribution. So you can parameterize this distribution, a number of Fourier coefficients. I'm sorry you can't see them so clearly. There's V1, V2, blah, blah, blah. And these denote the variations in the momentum distribution, which could be understood as coming from the initial flow moments. Okay, so these are called flow moments. And you can actually, they measure them. So these are results from Elise and Atlas for several of these flow moments as a function of how central the collisions were. So if you have two nuclei and they collide at the edge or they collide head-on, in one case, you have a small almond, which is the fireball, which is so it's highly anisotropic, or you have something more spherical if there's a head-on collision, right? And so depending on that, you get very different flow anisotropies in the collision. And so this is as a function of the centrality of the collision. So for the most central collision, it's like a sphere, it's like a circle. And then as you go further, it's more like an almond. And so if it's an almond, you should have more anisotropy. And indeed, that's what you see, that it grows. And so these data, these plots are actually hydrodynamic simulations. Okay? So this was done by myself and my colleagues. And we found that the viscosity entropy rate ratio is extremely small, okay, from the Elise experiments. And then you can also look at these as a function of momentum. You can look at a lot of different external parameters. And hydrodynamics works really beautifully, much better than you would expect in such a small system. Okay? And that's why I call it the unreasonable effectiveness of hydrodynamics in describing, to paraphrase Eugene Wigner, who talked about the unreasonable effectiveness of mathematics as a description of physical reality, right? So, and so you can also compare results from RHIC and the LHC, and you see that the viscosity to entropy ratio at RHIC is a little bit lower than that at the LHC, and this suggests that there's a temperature dependence of eta or S. Okay? And so these data, these are not from experiment, they're from various different models employing various strongly coupled techniques, functional renormalization group. There's some lattice results as well, but the lattice results are not very reliable because these are autocorrelation functions. They're not Euclidean correlators that you're actually measuring. So there's some uncertainties there, as well as, resummed perturbation theory and so on. So there's quite a bit of ongoing work in trying to understand the strongly coupled nature of the Quark-Gluon plasma from the results from experiments. And so here are some kind of Bayesian analysis of all the combined RHIC and LHC data of eta or S. And you see that it's really quite small, okay, as a function of temperature. There's some uncertainty, but again, this is the scale you're looking at. So this is 0.1 to 0.3. Now there's also a bulk viscosity, which is zeta or S. So that tells you that the fluid is actually not a conformal fluid. So there's violations of conformality because in a conformal fluid, you expect the bulk viscosity to be 0. But it's actually, it's not very large. Okay, so yeah.
Signature of, people try to
Right.
think of this as some strongly tracked formal theory,
right.
First approximation. Is there any other signature which goes in that direction? Experimental.
Yes, I'm going to actually come to that a little bit in terms of looking at the properties of jets. So in fact, so what you can, so it's good segue. So if you think about these very heavy ion collisions now at the LHC, you can really see jets being created. So this is in a lead-lead collisions, and you have dramatic events. Like you can also look at photons, which are then correlated with jets going through the Quark-Gluon plasma. So it's really studying the medium response to these things here. And so what's happening, right? So you think of a quark or a gluon that's moving jet that's going through the medium. It can radiate, and then it can interact with the constituents of the medium. Okay, so whatever their properties are, and so in the vacuum, the jet corresponds to collinear radiation of a large number of quarks and gluons which live within the jet. So that's what characterizes. So it's the energy flow that's within a jet. But now if you have a medium, that's going to kick out particles from the jet. And in fact, the slowest and the softest objects within the jet are the ones that get kicked out the most, while the hardest particles would just keep going. That's what asymptotic freedom also teaches us. Okay, so you have large angle radiation of the soft constituents. And now with the LHC, you can really do jet tomography. You can look at the fragmentation functions within these jets in these heavy ion collisions. And you see that the soft stuff gets modified much more than the hard stuff. And that is then giving you insight into, you have a very well-calibrated probe that's going through. You can compare it to what's going on in proton-proton collisions. You can look at photons or Z bosons as well, and that produces additional calibration of what's going on in these events. And so what you see remarkably is if you look at the ratio of the energy loss, of the jet, so there's a variable you can define that's a normalized ratio of the rates in a nucleus-nucleus compared to a proton-proton collision. So one would be if there was no quenching. So this is data from, say, photons. So photons don't interact with the medium. These are isolated photons. You see there's no quenching for the photons. But then now you see this tremendous suppression. Okay. And the reason you have the suppression up to such large energies, so this is 100 GeV jets, is because that the jet doesn't remain the same. The soft guys go out. So naively, people thought, oh, jet quenching would go away as you went to higher PT, but no, you're always modifying the jet because the softest guys are going to get kicked out. So there's a suppression. And so this is data from Atlas as now as a function of centrality. As the almond gets broader, also you see that you get more and more jet quenching because the size of the medium through which the jet is going through is larger. So you see that for the most central collisions, you get the greatest suppression. So now we have control, just like in condensed matter experiments of strongly correlated systems, of a number of finely tuned observables at the LHC that one can vary systematically. So even though we don't have a theory of the strongly coupled matter, just like in condensed matter physics, we can come up with inspired models which will then be tested against all these different variables. So they have been, to answer your question more specifically, there are sort of models which also use ADS QCD or ADS CFT. I think many of them are rather not, they're a little bit further from theory than one would like, but I think they're inspired by, sort of like soft breaking of conformality and so on. There are various ADS QCD models that actually do that. I think that the evidence is mixed on whether they describe the data. I think it's very challenging for most models, including weakly coupled descriptions, to describe the data. So yeah. Right.
At some point, I remember seeing some lattice data of the
right.
energy. Just
right. But yeah, this is a transport coefficient. Yeah.
98 that of an ideal gas.
Right. That's
so
that's
that was some signature, maybe
right.
that there was a strongly interacting kind of conformal
so
there is some transport analog of that.
Right. I think with transport it gets more challenging. I think with what you're talking about is there was a prediction by Gubser, Klebanov, and Polikov that the free energy of ADS-CFT would be 0.7537. It was close. The biggest problem for this is that there's strong breaking of conformality. So if you look at the pressure minus 3 times the energy density around TC, there's a big bump. So in the region where you expect strong coupling to be most effective, you see a huge breaking of conformality. And the breaking and the restoration is consistent with its restoration due to asymptotic freedom. So yeah.
To around 300 MeV, where you're not yet in the free.
Yeah, so there have been people who have been trying to.
Bulk viscosity plot.
Yes. So there's always a bump, and so you could argue that there is a conformal region, which is where or nearly conformal region where you could understand it as kind of coming from, but you have to then understand that as not being due to the natural restoration of asymptotic freedom. So there's a subtlety there. But I think it's very much still, an open thing. But my point is that there's a tremendous amount. So you come up with an idea, you'll be immediately confronted with a whole range of experimental data, which will test and I have had ideas killed by CMS and Atlas. So I think it's a very humbling experience. I can tell you that. So in my last, I'm running over time. I think I started a little bit late, so I'll have a couple of minutes. So we've talked about, the Quark-Gluon Plasma. It's a perfect fluid, and there are all these remarkable probes of both the bulk properties and transport properties of the Quark-Gluon Plasma. But there's this really outstanding question, which is, how does this object thermalize in the first place? Why this unreasonable effectiveness of hydrodynamics? And so, and I think many of these issues are also similar to the kind of questions one asks in the gravitational black hole kind of context. How do you generate the entropy? This is very highly occupied matter. How is entropy generated? How does this very strongly occupied stuff go towards thermalization? Is there some kind of scrambling phenomenon, decoherence? There's a very rich field there, which is, again, hampered because we're in 4 dimensions, 3 + 1 dimensions, and of course, we have confining strong coupled physics. But the questions are still, nevertheless, very pertinent and can give us insight into quantum field theories in general, and in terms of how to think about such strongly correlated or coupled regimes. And now we have experiments which, like for example, if you measure photons and jets are sensitive to the entire time scale of the evolution. So I had this plot, and I didn't emphasize it, that a jet is formed very early because it has a very high energy. So by the uncertainty principle, is formed almost at the instant of the collision, and it traverses the entire medium. Right? So if you were to study this, changing the centrality or changing the energy or changing various other triggers, you become more and more sensitive to what's actually going on here. So we're kind of going beyond the stage of saying, well, hydrodynamics works, to asking why does it work and where does it break down? Can we look at hadron collisions at high multiplicity and explore this dynamics? So that's a kind of a very rich field, and there's a program at the Kavli Institute this in a few months, which will kind of discuss some of these issues there. So there's a kind of a canonical picture which has emerged, which actually does a fairly good job of describing the data, where you can think about the matter as these colliding gluon shock waves, which kind of decohere, and then there's a very interesting. You can do simulations of overoccupied classical Yang-Mills systems, where you see that the system actually approaches a kind of non-thermal attractor. So that's a very interesting kind of behavior you see, whose dynamics is universal to ultra-cold atomic gases. So there's an interesting possibility that you could use cold atom simulators to really mimic some of the properties of overoccupied Quark-Gluon plasmas. And then there's also kind of a very rich evolution from such attractors. So this is weak wave turbulence in play, to hydrodynamic attractors as well. So there's a whole discussion from ADS-CFT as well of how you would have hydrodynamic attractors eventually forming this. So there's a lot of ideas floating around. If you're interested, I have a review with some of my colleagues where we discuss some of the ab initio approaches and some connections to other fields. So at the very end, this kind of dovetails into an argument for really understanding QCD, not just as the theory which is made up of partons and so on, but really as a strongly correlated theory of strongly correlated quarks and gluons, with very rich many-body features, just like in condensed matter physics. After QED was formulated, and so it led to this whole interesting field. Of course, we don't have tabletop experiments, but the Electron Ion Collider will be kind of the closest thing we have to a tabletop experiments, because it'll have intensities which are 1,000 times that of a previous such collider. And so you'll be able to really study many body states with very high precision. So you really can look at many body correlations of quarks and gluons, which are separated spatially, and in momentum and so on. And so you can really start asking questions about, what is the space-time structure of the quark-gluon matter inside hadrons? So we had some discussion about confinement, and this would be a place where really clever ideas for extracting what is the spatial distributions of quark and gluon degrees of freedom inside the hadron are. So as you vary energy and so on, can we, from bottom up, create a picture of confining dynamics at high energy? So that would be a dream for me, is to come up with effective models, theories, which can kind of capture that dynamics. So that's a way to actually make progress on confinement, which I rarely hear from sort of more formal-minded approaches, but this is kind of a more bottom-up pedestrian way, which requires an equal amount of ingenuity as anything else in terms of thinking about really clever experiments, which will explore, many body correlations, entangling dynamics, and so on. So QCD is not dead; it's very alive. And thanks to David, I think we have a very bright future in understanding strongly interacting matter. So I'll end by saying that we have discovered this unicorn with its many beautiful features, and we have built a corral around this thanks to asymptotic freedom and confinement. But hopefully, it's not the end of the story, and there's much that remains to understand it fully. And thank you for your patience.
Thanks very much for taking us through the modern view of QGP. And any questions, comments?
Yeah, so I had a couple of questions. One is like, okay, you are comparing the viscosity to the entropy, right? So one is it like a transport coefficient, the other is like a equilibrium quantity, right? And then you had like two time scales, like a relaxation and a quantum. So where are these two? And because for the viscosity, I can imagine there's a relaxation time scale. Where does this other? Why is there another time scale? I mean, because it's entropy is a purely equilibrium thing, right?
Yeah. But if you think about this in some kind of a kinetic picture, right? So imagine that you had a gas of quasi-particles or billiard balls, and you were kind of scattering these against each other. So that's the variables that you would be relevant, because the thing that would matter is what is the size of these objects that are colliding, and how strongly are they colliding with each other. That would determine how quickly the system thermalizes, for instance. Right? So you start with a system which is out of equilibrium. It's a bunch of quasi-particles. You solve the Boltzmann equation or your favorite molecular dynamics picture model, and then you see how does the system go to thermal equilibrium. And in fact, that's what people do when they try to estimate the viscosity of other fluids.
Yeah.
Molecular hydrodynamics, for example, that's the way people actually extract viscosities of various fluids. Yeah. Right. Yeah. Also, the other time scale comes in when, so for most fluids, it's almost irrelevant because they're very dilute. But when you get to really strongly correlated fluids, where the separation timescales are on the size of the de Broglie wavelength, and it's not even clear you can use this molecular hydrodynamics picture at all.
So right? It's a relativistic system. So the de Broglie wavelength translates into a time scale.
Yeah. So the wavelength. Yeah. So I don't know if that was your question, but yeah.
Because it's relativistic.
Yeah. Yes.
No. The de Broglie wavelength is a de Broglie wavelength. Right. I mean, that's just what it is from the occupancy. I mean, that's an equilibrium if you wish. But that translates into a time scale in a relativistic system.
So I think
because length scale
is... so another way to think about it is to say that it's a ratio of the mean free path in your system, right? Relevant to, what the interparticle spacing is, right? So if the interparticle spacing is comparable to the mean free path, then the concept of a mean free path itself breaks down. And that's the nature of these strongly correlated coupled fluids. So you had another question.
And one question is like, where is how do you get entropy reduction? So usually, like for ideal gases, you get shocks or regions where there are high gradients, and there, the viscosity becomes important as you get dissipation. So is it possible, like even though you estimate that the issue is really small, but it might there are regions of high gradients where like shocks and so on, like there you can get.
Right. So when I'm talking about entropy production, it's in a slightly different context. It's really what you have is you have the collision of really pure states. They're these hadrons, right? They have zero entropy. Right? But then you can think about these as quantum objects, right? Which have large number of degrees of freedom, right? That make up its constituents. These are quantum fields, right? And so essentially, then the question is, how do you go from this kind of pure state configuration to one where you actually generate entropy, and how do you think about such objects? So it's really sort of the very nature of particle production to start with. Then there's of course the viscosity associated with once you produce all these particles, then how do they reinteract and scatter and so on. So that's a separate set of questions, which is kind of the late stage picture that I was pointing out. I'm talking about how do you create entropy in the first place, and what does it mean? What are the right degrees of freedom when you have such highly occupied systems? So you're producing, in an LHC collision, you're producing 10,000 particles, okay? And they came from a few Fermi, right? So how did that happen? What is the dynamics inside these objects? So for instance, there are proton-proton collisions of the LHC where you produce 200 particles. And a proton is the size of a Fermi. So you have these extreme events where you can trigger on 100 particles in final state. So how did 100 particles emerge from such a small object? Okay. And that is kind of an extraordinarily interesting question where you can study the correlations of those particles, the many-body features, and so on, and try to understand how this process occurred. And that's going to give us deep insight into the nature of the theory itself. How does entanglement take place between different space-time regions inside the hadron, for example, which may be reflected in these final state correlations. So there's a set of general quantum field theoretic questions on the entangling properties of gauge theories and so on, which are all actually being reflected in these experiments, and the challenge is to connect to this deeper physics. Yeah.
Yeah, did I hear you right that compared to earlier times with the initial RHIC experiments, now there are many newer ways of tuning experimental parameters, and there are finely tuned observables which. So can you explain? I mean, very simplistically, I thought that in RHIC, you have two disks which are colliding at a certain energy. That's one parameter. And how off-center they are, that's the other parameter. Well, now you have many more. So can you just explain?
So for instance, if you vary different systems, you can vary at RHIC systems from hydrogen to uranium. Okay, they have very different geometries to start with, right? And so then depending on that, you can extract also its ability to process a huge amount of data. So you can actually look and you can trigger, so you can say, I'm just going to look at a class of events which had 500 odd particles or 300 odd particles. I can put in triggers, and then I can study what is the nature of those final states. And your theory or model better be able to describe that. So it's a multiplicity distribution. So essentially what you're doing is in a quantum field theoretic sense, you're really getting information on the generating functionals in some sense, right? You're not just, you're measuring the n particle probability distribution in a variety of different contexts. Also, you can study as a function of the momenta of the particles, right? You make cuts in the momentum distributions of the particles. You can look at different flavors. How many charm quarks are in an event? How many bottom quarks? What is the suppression of bottom 2s versus bottom 1s or 3s? That has been measured. CMS sees a very striking thing. As I mentioned, you can also look at top quarks in heavy ion. So the ingenuity of our experimental colleagues has been astonishing, I have to say. I mean, it's really, I would never have predicted, you know, this level. Yeah. Yeah.
Much the initial state, but you have enormous handles in the final state.
Yeah.
And
But even the initial state, we can vary the energies. Yeah.
energy.
Right. We can look at different species.
Atomic number, very limited. But the final state, hundreds of thousands of.
Exactly. And that's because of QCD, right? You produce strange quarks. You can, for instance, you can look at lambda correlations. And the lambdas are very important because they have weak decays. So if you open the Feynman lectures, he has a chapter on how you can measure the polarization of lambdas. So you can look at lambda correlations. And I have a paper, you know, where we say that, you know, this is a way of testing, you know, quantum long-range correlations, for example. You can see, if you look at particles in one phase space of the detector, are they correlated with things in the other region of the detector? Are there long-range correlations? It's just enormous, the amount of thing. So I think what it's really missing is really clever theorists who really engage with the data. That's what's missing.
As clever as the experimentalists.
The experimentalists have done their job, actually. And so I think what it's really missing is,
there are lots of people waiting outside.
Sorry.
You had a table, with comparing quark-gluon plasma and these cold atoms. So you had temperature and so on. So in typical these lithium cold atom experiments, there are about 200,000 atoms, a couple of 100,000 atoms. So what is the analog in the QGP thing in terms of number of particles and things like that? Or is it something?
Yeah, you measure the number of particles that come out in a given event.
And so what is the order? Is it similar order?
Oh, so the total number, say in an LHC experiment, typically is on the order of 12,000 particles. So, but what you can do is if you look in the detector, the particles are produced in some region in phase space like this. So you can actually look at how many particles are produced here, how many particles are produced there. That's in a variable called rapidity. And then, that's, of course, divided by the whole phase space. So you in per unit rapidity, you'd have about 1,000 particles or so, 1,500 particles or so.
Okay. I think we have to cut things short here because
people
are waiting.
Something else.
There's an interaction now, which you're welcome to stay back for, but primarily students and postdocs with David. So we'll have it right here.
Right.
So let's thank Raju again for a nice colloquium and safe journey back, and hope to see you again.